Hello, my name's John Broadwell. I'm the creator of the Serial Wombat open source project and also an embedded systems consultant at my company, Broadwell Consulting Incorporated, focused on medical device development and embedded systems design in general. If you need help with one of those areas, give me a call. Today we're going to be looking at one of the new features in the V212 version of the Serial Wombat 18AB firmware that pushes that chip farther towards being not just a smart I/O extender, but a embedded systems coprocessor for your Arduino or Raspberry Pi. And what we're going to be looking at today is a function of the processed input submodule, which is available on most of the Serial Wombat 18AB's pin modes that are inputs. So let's take a look at a Arduino sketch real quick to see what's capable in previous versions of the Serial Wombat chip. In this sketch, we're going to set up a joystick, which is an analog input, and a servo, which is an output, and we're going to use the Serial Wombat's output scaling function to tie the output of the servo to the input from the joystick through the Serial Wombat chip's internal firmware. Through our loop, we're not actually going to make any changes. And we can see I've got a servo circuit set up over here. And if I move this joystick down, the servo moves one direction. If I move it up, it moves the other direction, and it moves proportionally with the position of the joystick. And the Serial Wombat chip is handling all this. And this is very useful. This would be spectacular if we were trying to drive a car, for example, or perhaps pan a camera or, target a laser or something like that. But that's not always what you want. Imagine for a moment that I have a robot arm at the end of this. Every little twitch of my finger moves that robot arm. And if I had 5 or 6 different servos, I'd have to hold 5 or 6 different inputs all in the same place. So it's not particularly good for that kind of input. The input integration transform of the Serial Wombat processed input module is designed specifically to handle this kind of criteria. Let's look again real quick at the processed inputs aspect of the Serial Wombat chip. The processed input is a block of functionality that can be attached to the raw signal that comes off of any of the Serial Wombat's variable inputs, such as the ultrasonic distance sensor, pulse measurement, analog input, cap touch, resistance measurement, things like that. And a signal comes in and goes through a series of optional blocks: outlier excursion, inversion, transform, output filtering, and averaging, and then is ultimately output to the rest of the system or to the Arduino as a 16-bit value that has been pre-processed inside of the Serial Wombat chip every 1 millisecond. We're going to be looking at the transform block today. And the transform that we're specifically looking at, there are a number of different ones, but the one we're looking at is Input Processing Integrator. And the purpose of this is to take an input, such as an analog input, and essentially break it into 7 different zones that change the value of that 16-bit value in proportion to how far from the center the input has moved. So for instance, on a typical joystick, we're going to have an area at the top where we want a dead zone. And we don't want that to just be the exact middle, because a lot of times when you take an analog joystick, you push it to one side and you let it come back to the middle, it doesn't come back to exactly the middle. And anybody who's ever had an Xbox controller or a PlayStation or whatever that gets some drift in it knows that you need to have a good dead zone in the middle. And so for starters, you'll be able to declare an area between which the output of the input processing block does not change. Then typically you want, as you move that input farther one way or the other from the center, you want a faster rate of change. And a lot of times for applications, particularly robotics, you may want one area that is very precise change. Perhaps we're trying to get a robot arm to exactly get in the right spot to grab an object. But sometimes you want to move far from one end to the other, and so you want a rapid change. And the Serial Wombat firmware anticipates that. It lets you set two different parameters, one fast, which is over at the edges, one slow, which is for precision movement, and in between these points, it does interpolation. So, for instance, suppose that your rate of change at this index is 10, and at this index is 100, halfway in between, it would be 110 divided by 2, which would be 55. At the dead zone, it is 0. If it's 10 here, if you put the joystick in this position, it would be 5, halfway between the two. And so on in the other direction, where instead of incrementing, it would decrement. Let's take a look at an example that uses the joystick in this manner. Here we have a system diagram of the circuit that you saw earlier. And in this case, we have a joystick that's coming in on an analog pin, number 19, and being processed by the analog pin mode. We're going to hook up a TM1637 display so that we can display the position of the servo as a number. And we're going to hook up the servo that will take that 16-bit number generated inside of the Serial Wombat chip and output it to the servo. And again, all of this is designed around the idea that you want to offload as much functionality to the Serial Wombat chip as possible. But at any time, the given Arduino or Raspberry Pi or whatever could shut these off and take direct control of the servo based on the input from the joystick, if so desired. So let's look a little bit closer at this. We're going to go in, and every 1 millisecond, we're going to get an analog input reading. And we'll feed that into the pin 19 input mode. And it'll go through outlier exclusion, which we're not using. We're not going to invert, but we're going to run it through this transform. And that transform will integrate the net amount of left or right indication that we've given up to that point and output a steady value that goes up or down depending on which direction we hold the joystick. And then at that point, that value within the Serial Wombat chip will flow to pin 15, which is controlling our servo, and it will flow to pins 16 and 17, which are controlling the TM1637 based on our configuration. So let's take a look at the code for that right now. If we go under File, Examples, Serial Wombat, 18AB, Input Processing, and Integrator, you'll see this example. And so in here, we're going to include Serial Wombat.h. We're going to declare a Serial Wombat chip. We're going to declare an analog input, a servo, and a TM1637 display. We'll set up our I2C bus and verify that there's a Serial Wombat chip out there, print out its version, and then come down here. Joystick, which is an analog input, we're going to say begin that on pin 19, and we'll just use the standard parameters for that. And then for Joystick Configure Integrator, we're going to tell it where in the 16-bit range that comes off of the analog input we want the output to be. So the up to 500 is all the way to the left. And I often don't want to put this, we could put this all the way down at 0, but if I've got a joystick that's not exactly right, we may not be able to hit that edge if the joystick doesn't go edge to edge on our reading. Then I'm going to declare a couple of numbers in between. It's important to know that 0x8000 in hex is the halfway mark. So 7000 hex is 1000 below that. 9000 hex is 1000 hex above that. So we've got a dead zone from 7000 to 9000. Then the distance from 500 to 4000 and 4000 to 7000 gets split up into the slow and fast zones. And then we're going to say, what do we want our increments to be? We're going to have them go 5 counts every millisecond in the slow range, 20 counts every millisecond in the fast range, and we'll initialize the value to the middle, 32768 or 0x8000 as the initial output. Then as we move the joystick one direction or the other, the output will go up or down from that initial value. We're going to say joystick write process input enable and turn on the input processing. It's off by default. We're going to say servo attached to pin 15. And we're going to write scaling enabled, which in this case, we're not doing any other specialized scaling operations, but we are saying, hey, servo, instead of being commanded by the Arduino, you're going to take your input value from pin number 19. And then finally, we're going to set up a TM1637 to display the 16-bit number representing the position of the servo, which is the output of the integrator. I'm not going to go into all of these parameters. There's a video up above here, if you look, that will link to the TM1637 guide. And again, in our loop, we're not actually going to do anything except we'll read the public data from the joystick and print it out to serial, just in case we want to see it actually operating. So now at this point, let's load up this sketch and see it run. So this is the circuit that we saw in the diagram. We've got our joystick over here. We've got our servo. Our servo is being powered from 5 volts. It's always good to power your servo from a different power supply than your USB port, because you don't want that noise on your USB port. You don't want that noise in your electronics, your digital electronics. So this particular little board that you can see here is available on Amazon. It's something I sell. Basically, it just takes the 5 volts from this battery and makes it available to the servos, and then also breaks out the servo signal pin so that you can easily connect it up to your Serial Wombat chip or Arduino or Raspberry Pi or whatever. So you can grab those boards on Amazon. I find them to be really convenient. They're not the best for power consumption. I have a heavier dutier board for that allows you to hook up to a power supply or a big battery, and it'll carry more current. But for little applications like this is really convenient. So you might want to look that up. We've got our Arduino over here. This is a SAM21D SHAO. Doesn't really matter, because anything that can talk over I2C is going to drive the same result. So at this point, we can see that it's gone through its initialization, and we have 32768 on the display. If I push the joystick down, we could see that value go down, and we're in the slow range. So it's moving slowly, and I'm just a little bit off of center, and we can see that I can control the joystick control the servo with great precision with that joystick. Now, if I pull it all the way to one end, we go into the fast mode, which moves the joystick much more quickly. So if this was a robot arm, for instance, I could move it to about the position I wanted, then gently nudge it back and forth. And then when I let go, because this is an integrator and we're in the dead zone, this output number doesn't change. So that's a lot different than the point where I was directly controlling the servo from the joystick. It was mimicking the position, and every time I let go of the joystick, it would go back to its center position. So I hope you can see how this could be quite useful for certain types of user interfaces. The ability to offload all of that sampling and integration to the Serial Wombat chip, even if you weren't having the Serial Wombat chip directly drive your output. If you were going to take that value and then send it over a radio link to a robot or something like that, especially if you had, suppose you had 4 joysticks and some buttons, each set of pins that you set up to this mode gets its own separate integrator. So, you would just cut and paste that code a few times, and you don't have to worry about synchronously sampling that joystick, adding and subtracting from your integrator, things like that. So, this is, again, just one of the tricks in the Serial Wombat's bag with regard to making it really easy to generate complex user interfaces. So those of you who've been around the Serial Wombat chip environment long enough, one of the things that I try really hard to do is to create congruent interfaces for different inputs that at some level, even though they're different on a physical level or a signal level, kind of become the same. And so let's look at how we can implement that exact same thing, feeding this rotary encoder into the input processing instead of the joystick. So in this case, we're going to get rid of the joystick, and we're going to go to pins 5 and 6 and use those to read a rotary encoder, also as an integrator, not as a direct position, and output it to the servo. So let's take a look at the code for that. Again, if you go under File, Examples, Serial Wombat, 18AB, input processing integrator, and under here there's integrator rotary encoder servo, which this sketch is awfully similar to the other one, except we've gotten rid of the joystick and now we have a rotary encoder, which we're going to initialize on lines 5 and 6. This particular encoder works perfectly with the default positions. Yours might vary. And we're going to change it so that the rotary encoder, this is another new feature in version 2.1.2 based on user requests, can go from 0 to 6. And if you try to turn it past 6, it won't go any farther. If you try to turn it left to past 0, of course the physical pin will click, but it won't continue to decrement the position. So the options we have are 0, 1, 2, 3, 4, 5, and 6, a total of 7. And we want that to be an odd number because the number in the middle is going to be our dead zone. We're going to have 1, 2, 3 to the right of the dead zone, 4, 5, 6 to the other side, and this middle pin will be one value that represents our in zone, our dead zone. So again, you can see the configure integrator. It looks awfully the same, except in this case, we're going to say 0 is our negative max, 2 is our middle. So 1 will, if the number 1 happens here, it'll split the difference between the slow increment and the fast increment. The average of 40 and 5 would be about 22. So at value 0, it will decrement by 40 per millisecond. At value 1, it'll decrement by 22 per millisecond. At the mid-index, it will decrement at -5. At 3, that matches our dead zone. So at 3, the integrator will not change at all. And then as we come down the opposite side, 4 to 6, then it does the same thing, except instead of decrementing, it increments. And again, we're going to enable processing enable. This other code has totally not changed. We're just going to display the integrator, except for, well, it did change just a little bit because we're getting the value now from pin 5, which is the rotary encoder controller that we set up, not pin 19, which was the analog. And again, nothing is happening in the loop. So let's upload that sketch. And it immediately went to position 0 because the rotary encoder started at 0. So I got to go a couple of clicks to get back to the middle. Then you can see as I go, right here is the middle, which would be our position number 3. And if I go 1 to the right of 3, it starts incrementing. You can see that servo moving slowly. If I go farther, it moves faster. And we'll go back to the middle. You can see we stopped at position 59,000. If I go all the way to the left, it goes quickly. Then I'm clicking back to get to now I'm at my dead zone, and I move to the right. And so what I have now is a rotary encoder with 7 different positions that can incrementally control the position of that servo. And so again, you can see if what you had was a series of rotary encoders, this would be a really, really great way to control a robot arm, or perhaps any of a variety of other integrative style user controls where you want the user input to dictate a change over time as opposed to an absolute position. So that's all I have for today on this particular pin mode. Again, version 2.1.2, as of the time this video was created, hasn't been released yet. It should be out sometime in April of 2024. If your Serial Wombat chip has an earlier version of the firmware, then you'll need to update it. You can do a search in this channel for firmware updates, and there's a few different ways to do that through either the serial port or the I2C. So if it's after April of 2024 and you're using this pin mode for something, leave me a comment down below. Or if you've got questions or suggestions, hey, I see that feature, but it doesn't quite do what I need. Could you add this to that? I think other people might also find it useful. A lot of the features that go into the Serial Wombat chip are driven directly by user requests as I try to realize use cases that I didn't anticipate, and the product's gotten a lot better for that. So until I talk to you again, have fun, keep making stuff, and look for the 2.1.2 release of the Serial Wombat 18AB firmware, or hop over and buy a couple of chips on Amazon. The Serial Wombat firmware is available on GitHub and is constantly being updated. Subscribe below so that you can see the latest features and videos that come out as we fix bugs and add new features. The Serial Wombat open source project was created by Broadwell Consulting Incorporated. Broadwell Consulting Incorporated provides help developing medical devices with a focus on developing embedded firmware, which is compliant with IEC 62304, ISO 14971, and ISO 13485. As well as remediation assistance for products already in production. For more information, contact John at Broadwell Consulting. Support requests for Serial Wombat should be sent to help@serialwombat.com and will be answered on an as-available basis. Also, feel free to leave your question in the comments below.